Hello guys. So today I'm going to discuss the algorithm to detect the prime numbers. Okay. So you are given an array and you need to find which numbers are prime. Okay. So the algorithm is to detect prime numbers. Okay. So what you are given is you are given an array A which is 6, 2, 5 and 8, and your output should be a string output of 0110. So 6 is not prime, 2 is prime, so we set that to 1, 5 is prime, so 1, and then 8 is not prime. Okay, so first we'll start with the brute force approach. What is a brute force approach? We iterate through the array, and for each number we check if the number is prime. Now what is the time complexity of checking the number is prime or not? For that we divide that number for we divide that number with all the numbers between 2 to that number minus 1, and if it is divisible by any number, then that number is not prime. Okay, so that is our brute force approach. So for each number the method is prime, right? It takes O of n time, right? So for example, right, so for example, suppose we have number 6. If you want to find whether it's prime or not, so we check if it's divisible by 2, if it's divisible by 3, if it's divisible by 4, and if it's divisible by 5. If it's divisible by any of these 4 numbers, then we'll say that 6 is not prime and will return false. Is prime method will return false. So this method will take O of n time, right, to check whether it's prime or not, right? And we are also looping through the array. So let's say in this array our maximum number is 8. So for 8 we are going to check all the numbers. We are going to divide 8 with all the numbers between 2 to 7. Okay, so we are iterating through the array, that is n, and then we are, for each number we are checking if it's prime or not. That is nothing but whatever the max number is there in the array. Okay, we will call it a max A. Okay, and the space complexity is O of 1, since we are not using any extra space. Okay, so this is the brute force approach. Okay, let me write the approach. So what we are doing here is, for any number A, what we are doing is we are checking if it divides from any number between 2 to A minus 1. Okay, and if it does, right, if it does divides, then that number is not prime. And the time complexity for this solution is O of n into max A, and the space complexity is O of 1. Okay, so we'll just write a quick code for this one. Okay, so we have public, so we are returning string detect primes, and then you have integer array A. So what you are going to do, we are returning our result as a string, so we'll use string builder. We'll keep appending our result to this string builder. So string builder, then we are iterating through the array. So for integer I is equal to 0, I less than a dot length I plus plus. Okay, and for each number we'll check if it's prime, if that number is prime, that is A of I. If that number is prime, then we will append 1 to the result dot append 1, and else we are going to append 0. So that's that, and then we are going to return our result. We'll convert it to string and return it, and we are done. Okay, let's write our is prime method. Okay, so public boolean is prime, it takes an integer n, and then if n is equal to 1, you remember 1 is neither prime nor composite, so you immediately return false for n is equal to 1. Then you iterate from integer I is equal to I less than n, I plus plus, and then if n modulo I, right, if it's equal to 0, that means it's perfectly divisible by that number. So what we are going to return? We are going to return false, stating that that number is not prime. And if you are done with the for loop and if it's not divisible by any number, then we'll return true, stating that this number is prime. Okay, so that was the brute force approach. Now what improvement can we do to this approach? Okay, let's look at a suboptimal solution. It's not totally optimal, but it's a suboptimal solution to this brute force approach. Okay, so if you look at this method, is prime method, right, it's taking off n time. We can reduce this, right? So let's say, for example, okay, if we are given any number x, right, if x, let's assume we are given a number x and that number is non-prime, right, x is non-prime, it's not prime, right, then can you write x is equal to a into b? Yes, we can write that, right, and a and b is always greater than 1, so a is greater than 1 and b is also greater than 1, right? So a into b, can I write a into b is equal to square root of x into square root of x. What is square root of x into square root of x? It's x, right? So I can write this. So I can write that a into b is, so a and b, right? So at least one of a and b should be less than equal to square root of x. Okay, so let's see. So if a into b, right, if it's greater, right, than x, if a and b is greater than x, let's say, for example, if a is if a is equal to, let's see, let me write this, a is equal to square root of x and b is equal to square root of x, then we can get a into b is equal to x. What happens if any of this is greater than x, right? If a is greater than square root of x and b is greater than square root of x, what do we get? A into b will be greater than x, right? A into b will be greater than square root of x into square root of x, and a into b will be greater than x, which contradicts our assumption that a into b should be equal to x, right? So at least, okay, at least one of a or b should be less than or equal to square root of x. At least one should be less than. The other can be greater than the square root of x, but at least one should be less than equal to square root of x, right? So for example, if we have a 16, right, 16, right, then we can write 4 into 4. In this case, both a and b is equal to square root of x. But if we have, for example, if we have 10, right, then 2 into 5, right? So here, if you see here, right, So what is the square root? Let me take something else, like let me take 25. So if we have 25, then no, not 25, let's take 10 only. Okay, so if we have 10, right, the square root of 10 is 3 point something, right? So at least this is less than the square root of 10. At least one of them should be less than square root of 10. So here we have 2 which is less than square root of 10, right? So we can use this approach. So instead of looping from 2 to n, we'll loop from 2 to square root of x, right? And we'll see whether we are able to divide that number with any number between 2 to square root of n. So now what will be our time complexity with this approach? It will be n into square root of max a, right? And the space complexity will be O of 1, right? So this is a great improvement, right? But it's still not optimal. Okay, so let me write the code. The method detect prime remain the same. We are just going to change our method is prime. So public boolean is prime, and it takes an integer n, and then the same thing, if n is equal to 1, so 1 is neither prime nor composite, so return false. And then we are going to look from integer I is equal to I less than, I can do math dot square root of n, but every time the for loop goes around, it will calculate this math dot square root. It's an expensive operation, so I'll just do this I into I less than equal to n. I can also write like this, right, instead of writing the square root, right, to avoid the math dot square root operation. So now here, if n modulo I is equal to 0, return false, and we are done with the for loop. And then if we don't find any number that is divisible, then we return true. It's a prime number. Okay, so that's the suboptimal approach. Okay, now we are going to discuss the optimal approach. Okay, the optimal approach is a Sieve of Eratosthenes. Okay, it's a very complicated name. It's a Sieve of Eratosthenes. Okay, so what we are going to do in this approach is, suppose we are given any number. For example, let's say we are given number 12, right? We are given n is equal to 12, and we need to find whether this number 12 is prime or not prime, right? So what we are going to do, or maybe we need to find whether how many numbers are prime and how many numbers are not prime between 1 to 12, right? So what we do is, we start with number 2, then we mark all the multiples of 2 as non-prime, right? So we are given number 1 to 12, and we need to find which are prime and which are not prime, right? So we have given numbers like 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay, so we'll start from 2 because 1 is neither prime nor composite, so we'll say it's not prime. Okay, but then we'll start with 2. Okay, 2 is a prime number, so we'll mark all the number as, so if it's prime, we'll mark it true. Okay, so initially all the numbers are true. Okay, we'll mark all the numbers are, we'll say all the numbers are prime. Okay, we'll say all the numbers are prime. sorry, let's say all the numbers are okay. So we'll start with 2 and we'll mark all the okay, now 2, right? 2 is prime, okay? So we'll start with 2 and we'll say, okay, let's mark all the multiple of 2 as non-prime, right? So we'll go to 4, we'll say that that's not prime. We'll go to 6, we'll say that's not prime. We'll go to 8, we'll say that's not prime. We'll go to 10 and we'll say that's not prime. We'll go to 12 and we'll say that's not prime. When we come to 3, we see that 3 is prime. So we'll mark all the multiples of 3 as not prime. So the multiple of 3 is 6. It's already been marked false. It's not prime. 9, right? That is not prime. So we mark it as false. And 12, which is already false. Then we go to 4 and we see 4 is not prime. So we don't need to go and mark the multiples of 4 because the multiples of 4 are already marked by 2. 4 is not prime. So all its multiples are marked by a smaller prime number, which is 2. So we just skip 4. Then we go to 5, okay? We see 5 is prime. Let's mark the multiple of 5 as non-prime. So then 10, we marked it false. And we go to 6. We see 6 is not prime, right? So its multiples are already marked by some smaller prime number, maybe 2 and 3 or so on. So we skip 6. Then we come to 7. 7 is true. It's a prime number. Let's mark the multiple of 7. We are not going till 14, so we don't need to. 8 is not prime. So we will skip it because its multiples are already marked. 9 is not prime. Its multiples are already marked by 3. It's a smaller prime number. 10 is false. That's not prime. So its multiple are also marked by maybe 5 or 2. 11. It's true. So 11 is a prime number. So we have to mark its multiple. But we are not going that far, right? So now see, you got all the numbers marked correctly. Which one are prime and which one are not prime, right? So suppose you are given this array, right? Our initial array, what was that? 6, 2, 5 and 8, right? So what you are going to do is you are going to find the maximum number in this array. For example, you'll find the maximum number here is 8, right? So you'll find 8 maximum number and you'll create this structure, right? Maybe it's a map or array, just array with a boolean array. You'll create this structure and you'll go from 1 to 8 and you'll mark all the prime and non-prime, okay? And then you'll just iterate through this array and you'll just get the true and false value for each of this number because all numbers are less than 8. You just find the maximum number in the array and you will do this, right? Now here there is one small improvement that we can do, right? So suppose if we are here at 5, right? So we see that 5 is prime. So we are going and marking all the multiples of 5 as non-prime. But look at this. 10 is already marked false by 2, right? Maybe if we go here 15, right? 15 will already be marked as it's non-prime. And this is marked by 3, right? 10 is marked by 2. So another multiple of 5 is 20, right? 20 is also marked false by 2 or maybe by 2, right? And then the next multiple is 25. That has not been marked, so we'll mark that as false and that will be marked by 5. So if you see here, right? So instead of starting from 10, we can directly start with 25, right? So if we are marking the multiples of 5, right? So instead of starting at 5 plus 5, we can directly start at 5 into 5, right? So instead of starting at x plus x, we can directly start at x into x, right? That will save us some time, right? And the terminating condition for this, let's see. So that's how we are going to mark all the multiples, okay? Now, okay, so now what is the terminating loop condition for this. So if we are trying to find all the primes and non-prime for n is equal to 12, right? So one is neither prime nor composite, so we mark that as false. Then we go to 2. We see that is prime, so we mark all the multiple of 2 as non-prime. So we mark 4, we mark 6, we mark 8, we mark 12, and we mark 10 and 12. Then we go to 3. We see that 3 is prime, so we mark all the multiples of 3 as false. So 6 is already marked by 2, 9, we mark it false, and then 12, which is already marked by 2. But do we have to do this for all of these numbers? No. We just have to do till square root of n, which is square root of 12, which is 3 point something, so which is till 3, right? Because rest all numbers will be marked by these 3 numbers. So 4 is marked by 2, 5 is already prime, no need of marking, it's set to true by default. 6 is marked by 2, 7 is already prime, 8 is marked by 2, 9 is marked by 3, 10 is marked by 2, 11 is prime, 12 is marked by 2. So the numbers which are not marked, they are prime, and the rest of the numbers, they are already marked by this, right? Because you remember a into b is equal to 12, or a into b is equal to n, and a and b could be less than equal, at least one of them will be less than equal to square root of n, right? So we don't need to go all the way. So the terminating loop condition is square root of n, because all 9 non-prime, right, which are greater than square root of n will already be marked. Okay, so what is the time complexity of this algorithm? Sieve of Eratosthenes. So the time complexity of this algorithm is so for example, if you are doing for n is equal to 12, so it would be n into log of n, right? Because what we are doing is we are doing log n to mark all the multiples of n, right? And we are doing, so there will be 2 loops. The outer loop will go from 2 to square root of n, right? And then the inner loop will mark all the multiples till n, right? So it will be O of, so the time complexity of this algorithm is O of n into log n, right? That will be the time complexity, right? Now what is the space complexity? We need to maintain this, right, in some array or somewhere, right? So it's O of n, right? So the space complexity is O of n. This is still better than this one, right? So there was this approach. Now we are, remember what we are given? We are given an array, right? We are given this array 6, 2, 5, 8, right? So how we are going to apply this algorithm? We'll pick a maximum number from this, which is 8, and for 8 we'll construct this table and we'll mark all prime and non-prime numbers, and then for all of this we'll just do a get from this array, right? So this time complexity, this n is the maximum. We are doing only for one number, which is the max, right? So n is equal to, you can say it's max a or max underscore a, right? And the space complexity will also be max underscore a, right? Now this solution is better, okay, than the solution with time complexity. It is of course better than the solution with time complexity of n into square root of max a. It is of course better than this one, right, the solution, but it also depends on the situation, right? Sometimes we need to consider the space, right? So if we require O of one space, right, then if we don't need to consume spaces of concern, then we need to apply this solution, right? So when space is important than time, then we should opt for this solution. I know it's a little bit slower, but we should opt for this solution, right? So if we are given a single integer, okay, now let's see, right now we are given an array, right? But let's see if we are given just a single integer n, okay, and you just need to find if it's prime or not prime. What solution we should use? We should use this solution, this one, n into square root of, sorry, we should use this square root 1, right? So the time complexity for finding whether n is prime or not prime, so it would be just this square root of n, right? Because we'll iterate from 2 to square root of n and we'll be able to know if n is divisible with any of those numbers, then it's not prime, otherwise it's prime, right? So when we should use this algorithm, Sieve of Eratosthenes, it is helpful when many numbers need to be checked, right? And pre-processing can help, right? So when many numbers, we need to check many numbers, then this pre-processing thing that we are doing, it can help, right? And if those numbers are limited to a given range, right, we know the range, right? So we can estimate that how much space we require, right, for the algorithm. So in this problem, we are given a range of numbers, right? We are given this numbers, it's kind of a range, right? So we can apply this algorithm. But when you are given a stream of random numbers, I mean, we don't know, the array is not predefined, it's just coming, then stream of numbers, random numbers are coming, nothing is specified about the range, right? Then what you can do, if you are given a stream of random numbers, you are not given an array of friends, you are just given a stream of random numbers, then which solution is better, right? In this case, what you can do is you can use some caching, right? Caching is useful, right? Because what happens, right? Because the numbers, they are going to repeat, right? Because in real life, what happened? That's what it's likely gonna happen in real life, right? Because the numbers are going to repeat. So we can use caching. How we can use caching? We can maintain hash map, okay? We can maintain a hash map with the number and whether it's prime or not. So we'll have a number and whether it's prime or not prime, right? So we can maintain a hash map. So if we encounter 4, then we'll see, okay, 4 is prime or not prime. Oh, it's not prime, so we'll mark it false. Or we encounter 5, it is prime or not prime, so we'll enter it into the hash map, map it to true, right? So for each number, right, we can check in our hash map if it's present in the hash map, right, we are done, right? So we'll check in hash map, right? If present, then we are done, right? But if it's not present in the hash map, then which method will use to find find whether that number is prime or not prime? You can use this method, right? This one, square root of n, right? We can use this method to check whether it's prime or not prime, and then we can add it to the hash map, right? And you can improve the space complexity further, auxiliary space. You can improve this auxiliary space by checking that if the numbers are even, then we don't even need to add them to the hash map, because all the even numbers greater than 2, they are always not prime, right? So we can improve it, right? So it's just the discussion, okay? So let me write the code for this, apply this Sieve of Eratosthenes, and write the code for detecting the prime, okay? So let's say we have this, our public, we are returning the string, right, whether the number is prime or not prime. We are given array of integers, right? So we are given an integer array, and what we are going to do, we are going to find the max number from that array, okay? So that code is this, e of 0, and what we are going to do for integer value a, if value is greater than max, then max is equal to value right, and then So that we found our max number, and we need to have some storage, right, to store all the numbers till this max, right? We need to apply that algorithm, and we need to store it true false for each number from 1 to n, right? 1 to max. So we'll take boolean array only. I'll just take boolean array is prime, right? What is the size of this boolean array? That's the max. I think it's a max plus 1, right? Because let's say if the max number is 12, then we are storing all the numbers from 1 to 12. Array index starts at 0, so we disregard 0, but all the numbers from 0 to 12. So that's 12 plus 1, 13, right, size. Then we'll apply our algorithm, which will populate this array, right? We'll apply our algorithm, okay, and our algorithm will pass our storage and will pass the max number, okay, and then this our storage will have all the numbers, whether it's prime or not prime, and then you can build this result string. So string builder result is equal to new string builder for integer I is, let's do this, for integer value in array A, we'll just check in our storage is prime value. If it's prime, then what we are going to do, result dot append 1, right, and else result dot append 0. Then we are going to return our result dot to string. Okay, so now let's write this algorithm, right? We are going to apply this. So public void apply Sieve of Eratosthenes, okay, and then we have our storage boolean is prime, and then we have our integer n, max integer, right? So what we are going to do, okay, we are not going to look for all the numbers from 1 to n, right? We'll look only till root of n. So for integer I is equal to 2, first we'll set our storage everything to true, everything is prime. I less than equal to n, I plus plus. We are not setting 1, right? We are not setting 1 to true. It's not prime nor it's neither prime nor composite. So is prime of I is equal to true. Everything is prime, okay, but except 1, right? So we'll just set it manually. It's prime of 1 is equal to false, okay. Now we are going to loop only till square root of n, right? So integer I is equal to 2, I less than equal to math dot square root of n. But we are not going to do this operation, expensive operation method square root. We can simply write I into I less than equal to n, I plus plus, right? And we are going to mark all the multiples of I as non-prime, right? But we'll do only if I is prime, okay? So if this I is not prime, right, then we don't need to mark all the multiples of I, right? Because I is not prime, so all its multiples are already marked by some smaller number. So if I is not prime, right, then we just need to skip this loop. We need to move on to next I, right? I is not prime, right? Just like in this case right here, we saw when we came here, right, 4 was already marked false by 2. So when we came here, right, We don't need to go and mark all the multiples of 4 because they are already marked by 2. So we'll just skip the loop and move on to next number, which is 5. And this is our loop, okay, for marking all the multiples. So integer j, and we are going to start from, so when we are marking the multiple of 5, for example, I told you, right, we'll not start at 5 plus 5. I mean, we'll not start marking from 10. Why? Because those are already marked by the smaller numbers, like 10 is marked by 2, 15 is marked by 3. So what we are going to do is we are going to start from 5 into 5. That means we are going to start from 25. Okay. So for j is equal to I into I, and j less than equal to square root of, sorry, j less than equal to n, because we are going to mark all the multiples till n including n, j plus plus, right? And we are going to mark is prime of j. So all those are non-prime, so we'll mark it false. They are not prime. They are non-prime, so we'll mark it false. Okay, that closes this follow, sorry, this follow, outer follow, and then the method. Okay, so that closes everything. So that was the algorithm pretty much. So you can use this algorithm. So if you know the range, you can find the maximum number and you can apply this algorithm. Another problem that could be given is you are asked to count the primes. Okay, count the prime numbers. Okay, count the primes, and you are given an integer n. I'm just given an integer n. For example, I'm given n is equal to 30, right? And I need to count all the prime numbers between 1 to 30, right? So what I can do, I can just apply this algorithm and I can populate this table from 1 to 30, and then I can just look through this table and find which are set to true, and those are my count number of primes, right? So that is one more problem which can be solved using the same algorithm. And yeah, that's it pretty much. It's very simple algorithm. You just have to remember that you are just continuing till square root of n, and you are just starting from I into I. I told you, right, we don't need to start marking multiples from the next number I plus I. Instead of that, we will just start from here, right, because those are already marked, and we'll go till n, right? Thank you so much for watching the video, and I'll come up with some other problem next time. Thanks.